Hello everyone, and welcome back to another remote sensing lecture video. And in this video, I want to sort of recap what we talked about when we talked about bit depth and radiometric resolution. And I want to delve a little bit deeper into binary mathematics. Now, I want to be upfront and say that I don't expect you to follow the math entirely, but more so just see where certain things come from that will hopefully help solidify that framework of what radiometric resolution means, what bit depth means, and why bit depth has such a strong impact on data volume. Because I feel like I kind of sort of glossed over some of those points. And so what I want to do is I want to, first of all, when we talk about a bit, we're talking about binary mathematics. And for those of you that aren't familiar with binary mathematics, right, binary math, right? The idea is that you have what's called a binary digit. Ooh, hope if I could actually spell digit. You have what's called a binary digit, and you have the B from binary, and the it from digit gives you bit. Right? We were talking about 1-bit, 2-bit, 4-bit, etc. before. Right? This is where bit comes. It's sort of an abbreviation of binary digit. And so a bit in binary can have a value of either 0 or 1. And we talked about this when we talked about 1-bit. But then I sort of jumped ahead to 2-bit and I said, well, 2-bit can have a value of 0, 1, 2, or 3. But I want to sort of take a step back and walk through how we got there. And I think it'll help, again, solidify some of those principles. So if we have 1-bit, right, if we have 1-bit, right, that 1-bit can either be a 1 or a 0. And so with 1-bit, if it's 1, right, that's 2 to the power of 0 times 1, which is equal to 1. If it's a 0, that's 2 to the power of 0 times 0, which is equal to 0. Right. So again, I don't necessarily expect you to follow along with this math here. I just want you to sort of, that should actually be 0. 2 to the power of 0 times 0 is 1 times 0, which is 0, not 2. Right? So that's if it was 1-bit, right? The pixel value would either be a 1 or a 0. If we do 2-bit, right? Now we have 2 bits. We have a 1 or a 0 here, and we have a 1 or a 0 here. So this is 2 bits. Right? So now in 2-bit, right, we have 4 options. We could either have them both be 0, bit 1 and bit 2 be 0. We can have bit 1 be 0 and bit 2 be 1. We can have bit 1 be 1 and bit 2 be 0. Or we can have both bits be 1. And the order here is important, right? So if you think back to when you were learning how to do, actually you may never have actually been explicitly told this, but the reason that our base 10 number system works the way it does with tens, hundreds, thousandths, etc., is because of the fact that each sort of digit is a power of 10. Right? Well, in binary, each digit is a power of 2. Hence why I did the 2 to the 0 up here. So in this case, right, if we have 0 to the 0 and 0, 0, this is equal to 2 to the 1 times 0 plus 2 to the 0 times 0. And this is going to give us 0, right? This is going to be 2 to the 1 times 0 plus 2 to the 0 times 1. And this is going to be equal to 1 because 2 to the 1 is 2 times 0 is 0. 2 to the 0 is 1 times 1 is 1. So this is why order matters. Because in this case, right, we have 2 to the 1 times 1 plus 2 to the 0 times 0. So in this case, this is going to be equal to 2 to the 1 is 2 times 1 is 2, plus 1 times 0. So this is going to go to 0, and that's going to give us 2. Now in this case, right, this is going to be 2 to the power of 1 times 1 plus 2 to the power of 0 times 1. So this 2 to the power of 1 times 1 is going to be 2. This 2 to the power of 0 times 1 is going to be 1. So 2 plus 1 is 3, right? And that's where the 0, 1, 2, and 3 came from in the previous video when I said that if you have 2-bit, you have this list of options. So what I want to do here is I'm not going to go through all of the examples. I'm just going to jump down to, say, 6-bit, right? Right, for 6-bit, right, we have 6 bits. We have a 1 or a 0, 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 and a 1 or a 0, right? We have 6 bits, right? And so you can see here, as we go from 2-bit to 6-bit, right, we've added 4 additional pieces of information, right? We've added 4 additional sort of digits that we have to keep track of, right? And so if we want a 6-bit number to be 0, right, that's going to be, if we wanted this to be 0, we would have to do 0, 0, 0, 0, 0, 0, right? So in a 1-bit, right, if we wanted the value to be 0, all we had to do is keep track of one piece of information to get 0. Right, in a 6-bit, if we want the number to be 0, we have to keep track of 6 bits of information. And if we have 8 bits, we have to keep track of 8 bits of information. So hopefully this makes sense as to why, when we increase the bit depth, right, we increase the number of bits, right, we're increasing the number of digits we have to keep track of. So even if the number is 0, right, this number is 0, even if the pixel value is 0, we're still using the full 6 bits, right? It's not like we can just ignore the first 5 and go back to 1-bit, right? We still have to keep track of all 6 bits of information, even though the pixel value, the number that we see, is 0. So to sort of circle back to that point, right, when we were talking about how bit depth affects data volume and why we don't have everything being 64-bit or 32-bit, that's because even small numbers that could be represented with fewer bits, if you have a 64-bit bit depth, you still have to keep track of all 64 bits. So every time you increase bit depth, you're adding an extra piece of information that your computer has to keep track of, even if the numbers themselves don't necessarily require that full bit depth, right? Like in this case, this value of 0 here, right? We don't need 6 bits to represent 0. We can represent 0 with 1 bit. But because of the way binary works, we still have to keep track of these other 5 bits. And that's where that extra data volume comes from. Hopefully that makes sense. Hopefully that made things a little more clear. And as always, please feel free to reach out. Thank you.